In level 54, the task is to obtain metallic iron from iron 3 oxide, or iron ore. Addition of 3 moles of oxygen as a product into the receiver flask, and balancing the reaction equation, gives enthalpy change, delta H, plus 1,651 kilojoules. This is an endothermic reaction. Heat is consumed. Entropy change, delta S, is plus 508 joules per Kelvin. Positive delta S value means that the chemical system composed of iron and oxygen elements is less random when these elements are combined into iron 3 oxide, a reactant, and it is more random when they exist in the form of iron metal and O2. The products. Combination of these delta H and delta S values at 298 kelvins gives Gibbs free energy change, delta G, plus 1,500 kilojoules. It means that dissociation of iron 3 oxide into iron metal and oxygen is a non-spontaneous reaction. This also means that the backward reaction is spontaneous. The backward reaction represents oxidation of iron. Oxidation of iron, especially in the presence of moisture, occurs spontaneously and is known as corrosion. Positive delta S value means that it is in principle possible to achieve a state in which entropy factor will dominate, making delta G negative. Indeed, dissociation of iron 3 oxide into elements becomes spontaneous at 3,250 kelvins, or nearly 3,000 degrees Celsius. This is a very high temperature. Therefore, it is not practical to produce iron metal by dissociating iron 3 oxide into elements. In industry, most iron is produced in blast furnaces. Iron ore is mixed with coal. In the presence of oxygen, the reduction reaction takes place. This process may be described by a simplified reaction equation. This is an exothermic reaction with the delta H value of minus 710 kilojoules. Delta S value is plus 526 joules per Kelvin. This combination of delta S and delta H values gives delta G minus 867 kilojoules at 298 kelvins. This means that the reaction between iron 3 oxide, carbon and oxygen that yields iron and carbon dioxide spontaneous. Given that delta S is positive, in real blast furnace, the reaction of iron 3 oxide reduction is conducted at temperature higher than 298 kelvins. This is done to shift equilibrium towards the products to a greater extent, increase reaction rate, and intensify the process. Reduction of iron metal from iron 3 oxide is an excellent example to illustrate how one can convert a non-spontaneous reaction into spontaneous by coupling it with another spontaneous reaction. Let us look at this equation from a different perspective. We have just verified that dissociation of iron 3 oxide into elements is a strongly endothermic and a non-spontaneous reaction at 298 kelvins. Combustion of carbon is a strongly exothermic and spontaneous reaction under standard conditions. Adding left and right parts of reaction equation 2 and 3, and subtracting 3 moles of O2 from left and right part, gives exactly the reaction equation that describes iron production in a blast furnace. Therefore, coupling the reaction of iron 3 oxide dissociation into elements with the reaction of carbon combustion makes conversion of iron 3 oxide into iron spontaneous. In other words, reaction 2 is enabled thanks to reaction 3. One could also say that heat, which is released upon coal combustion, is used to drive reduction of iron 3 oxide. In a way, coal is sacrificed to convert iron 3 oxide into iron metal. This approach, coupling a non-spontaneous reaction which delivers the target compound with another spontaneous reaction, is common in chemistry. Explore this idea in ChemChallenge by using elements in their standard states, such as graphite, metallic sodium, hydrogen, as reactants. Energy is released upon their conversion into thermodynamically more stable species, such as carbon dioxide, sodium carbonate, and water. This energy is used to drive target non-spontaneous reactions.